So moving on, let's compare the heat transfer and friction coefficient behavior for turbulent flow and laminar flow. All right, so let's draw out here. Let's say we're going from 0 to x critical. So on the left of the plot is going to be laminar. On the right is going to be turbulent. And maybe actually let's say that there's a transition region, just to be clear. So this here is transition. And then here is turbulent. Okay, so what I want to do here is kind of show you how the heat transfer properties compare. So if we're thinking just about, like, let me just scroll up a little bit here. So remember the heat transfer from the surface to the free stream is dictated basically by the thickness of the boundary layer. How far does heat have to conduct across this boundary layer? So right at the leading edge at x equals 0, what is the thickness of the boundary layer? Right, it's 0. So right at the leading edge, there's infinite heat transfer, right? Which is kind of, I don't know, nonsensical, and it's not really what happens, but it's an approximation, right? So there's a huge amount of heat transfer because you have, in direct contact, two different temperatures. As you move further along in the x direction, that boundary layer grows. So then what happens to the rate of heat transfer as you move along? It's going to drop, right? You have this like growing resistance as the boundary layer grows. So thinking about that, if we were to plot the heat transfer coefficient right at the leading edge, what's that going to look like? Well, it's basically going to be infinite, right? Right. So right at the leading edge, our heat transfer is infinite. As you move in the positive x direction, what happens? Well, the heat transfer rate is going to drop. So you start seeing this, draw it a little better. So you start seeing the heat transfer rate drop really quickly, and then it starts leveling out as the boundary layer kind of grows more and more slowly. Okay, then at some point we hit this transition, and we start transitioning from laminar flow to turbulent flow. So in this transition region, what's happening? Well, look back up here. Our heat transfer is being dictated or governed by the viscous sublayer thickness. So you have this laminar layer, and then you start having the important thickness drop down to this little layer that's right next to the wall. So what should we expect to see? Well, there's a transition region where you're going to see the thickness dropping down. That's going to correspond to some increase in the heat transfer coefficient. And then the viscous sublayer is formed, and it's a really thin layer. And that's going to just sort of go along like this. Right? So maybe some subtle things here. One is the viscous sublayer going to continue to grow indefinitely? Right? Is this viscous sublayer going to continue to grow indefinitely? Yes. Why? Well, because the turbulent boundary layer is growing indefinitely. Right? There's nothing stopping the turbulent boundary layer from growing. So as long as that turbulent boundary layer is growing, the sort of shear forces in that boundary layer are dropping as it grows. The viscous sublayer is going to continue to react to that layer growing and slightly grow and slightly grow. Until at some point, maybe that boundary layer interacts with something else and you start getting constrained boundary layers. But at least in external flow, the viscous sublayer will continue to grow indefinitely. So as we draw it down here, this heat transfer coefficient here needs to continue to sort of slightly drop as you go. Other things to point out. The worst possible place for heat transfer is right here, right before you transition to turbulence. That is the worst possible place for heat transfer. What's the best possible place? Well, there's kind of two. One is at the leading edge in the laminar region, and the other is immediately after transition to turbulence. Right? Let's say you're designing a device and you want to maximize heat transfer. You put that device right after the transition to turbulence, and that's going to give you your best heat transfer. Okay? All right, so that's the heat transfer coefficient. We can kind of do the same thing for shear stress, so let's maybe draw that in a different color. So shear stress is going to behave really very much the same way. I'll just kind of draw it offset. But you have this kind of behavior where it comes over, starts dropping down to the transition region, then it ramps up, and then sort of follows the same behavior. So this would be tau S. That's our shear stress. Okay? Yeah, questions on this? Okay. So I think, yeah, question.
So is it usually lower than the heat transfer coefficient, or is that just to help see it?
I'm just helping so you can see it differently, yeah. I mean, these are actually in different units, so they're sort of plotted on different axes anyways. Okay? So turbulent heat transfer, takeaway, if you remember only a couple things of what I'm saying, which is probably what will be the case. Turbulent heat transfer is better than laminar heat transfer, except at the leading edge, right? Just remember that. Turbulent heat transfer is always better than laminar, except at the leading edge, yeah.
Since the turbulent heat transfer coefficient is decreasing, is there ever a point where it will be lower than the laminar?
Yeah, so good question. Would this thing ever sort of continue to diminish? In practical situations, no, right? Like this laminar, the laminar heat transfer coefficient is almost always going to be worse. I suppose if, yeah, there might be some limited cases where it does, but I would say almost universally that the turbulent heat transfer is going to be always better. Okay. Okay, so that's maybe a good comparison. So let's think now about how you actually implement this stuff. So we have spent some time thinking about this conceptual model. When it comes down to it, we want to really represent things accurately, not just using the conceptual model. So this is from the textbook, if you have the textbook. But this is a set of all the correlations for flow over a smooth isothermal, that is a constant temperature, isothermal, flat plate. So this is external flow. So what you can see is that there's kind of a number of different things happening here. But you have different correlations depending on whether you want friction coefficient, right, like friction coefficient here, whether you want the heat transfer behavior, the Nusselt number, whether you're looking for the local value, whether you're looking for the average value, whether the local or average, and whether it's laminar or whether it's turbulent. Right? So all these different situations come up, and you need to be very clear about what the situation is that you're looking for. If it's laminar flow, external laminar flow, and you want the local value, that would be, you'd be looking right here. So you kind of have to drill in and find specifically the correlation that you want. So let's, these correlations here, the local and average, these give you the kind of final representation of how you go from local to average. But it's actually not that tricky to do it yourself if you know the local function. So I just want to run through quickly an example of how you would compute the average from the local.